And if I now fix the parameters and compute the value of my function for a given possible realization of v, then one would call this the probability. So the probability of v given theta, and vice versa. If I fix v by, for example, taking the number that I got from some measurement, and I'm now looking for the parameter theta that best fits my model to the data or that best explains this observation, then I keep v fixed, and now theta is the function, and then this entire term becomes a function of theta, and in that case I call it a likelihood. Okay, so it's just it's the same equation fundamentally, but you call it probability or likelihood depending on which term in the equation you fix. Good, and now I want to apply this to the Gaussian mixture model. This is one of the not so many interesting models where EM, as described here, really goes through. In many other models, unfortunately, one of the equations is not tractable, or the model does not have a proper probabilistic interpretation, and then people will still call it EM style or EM type. So you often see iterative optimization schemes like we have just seen. But the Gaussian mixture model is really a pure application of that. So the Gaussian mixture model, or GMM for short, is a generative model. And you can generate observations as follows. You can randomly pick one of h possible mixture components, and you do that with a probability distribution over those mixture components, and then given a mixture component you compute a well, you draw a sample from a Gaussian distribution. So we have a generative model that comprises h Gaussian components, and graphical model notation would be as follows. So we have a vector of probabilities where j goes from 1 to h, and using this probability we randomly select a component. So from which, so to make this more concrete, let's say we have 3 Gaussian components, and to generate data from those I would first throw a dice, and the dice in this case would not have 3 equal sides, but it would have sides that are, well, weighted with these numbers here. So I would first say, okay, let's, for example, I'm picking this Gaussian distribution here, and now I'm drawing a sample from the Gaussian which could lie, for instance, here. So in this model, each observation that you have has a true provenance. It truly came from a single one of these Gaussian mixtures. But later on, we're just given a training set of points, like you saw in the example that I showed, and that I will show once more at the end of this hour. And here we have to somehow fit our components. So even if we first we have to try and guess how many components were in there, but even if we guess that right, once we estimate it, we're not quite sure if we're only given this training data here, this particular point, which let's say is this one here, which Gaussian component it came from. We can only estimate those probabilities. So which Gaussian component a particular observation was sampled from is a hidden variable, which, well, let me write it here as M I J. So that's the hidden variable that states which component J a particular observation I was sampled from. And now the actual observed value, so I can, in graphical model notation, I could shade this box to say that this is observed. This, so the actual value I observe depends on which component I selected, but it also depends on then the mean and the covariance matrix of this component. And we can repeat this a total of n times if we have n observations. So this kind of notation, I think what it means will become more clear when we talk about graphical models a week or two from now. But what I can write down is the density, so the probability of generating an observation X is, see, I'm integrating out this hidden variable. Is that. So pi was the weight of mixture component number J, and well, this was a Gaussian. I could use an alternative shorthand notation and say this is, you know, the normal evaluated at point X with these parameters here. So that's for a single observation, and now the log likelihood for a total of n observations is the log of the product of these terms here. I have this ugly summing out of the, or marginalizing over the unknown variable inside the log, which gives us all these numerical headaches. So I evaluate the distance between the ith observation and the jth Gaussian center. Okay, and theta here is the set of all my parameters, so it's all the mu j and the covariance matrices sigma j and these mixture weights pi j, where j runs from 1 to h for a total of h components. And we're now looking for the parameters that will maximize our likelihood. Subject to the following constraints, namely the mixture weights should be non-negative and they should sum to 1. And also subject to the constraint that my covariance matrix or covariance matrices should be symmetric and positive semi-definite. So they should qualify as proper covariance matrices. Yes? It was that's not the indicator variable of which Gaussian, it's a probability. Yes, exactly. So mixture weight is with which probability was any point sampled from Gaussian number J. Exactly. Oh. Okay. Left. So our hidden variable or the latent variable is which component generated an observation. And we now use the recipe we saw in the EM algorithm. So in the M step, we want to maximize following sum, which I previously also called energy term. This is our expected complete data log likelihood. And so I'm replacing this with my previous estimate for which Gaussian generated a particular point. Probability of xi and j given the parameters times my old estimate of g given j given xi. And the joint I write as a conditional times the prior. So I'm saying this is log p of xi given j, and the parameters times pi j. Okay, now making this explicit, I have all the formulas, knowing that this is a mixture of Gaussians. I'm assuming a total of h components. Now this is the distribution with which I am averaging. And then the log cancels with the exponential of the Gaussian. So I have directly the argument. Minus the log of the normalizing factor here. There we go. Okay, and I want to maximize this, so I'm computing the derivatives and of this beast here and setting them to 0. First, I differentiate with respect to the means of all these Gaussians, and well, I have a quadratic term here which will give me a 2, which will cancel with 1/2, and then I have 2 linear terms, also there the 2 cancels, so overall I get the following. In this I can finally solve for mu j, and I get the following. Good. This equation looks reassuring, because if you step back and look at it, it's see all of these factors here, they add up to 1. So this is a weighted sum of my observations, or it's because these factors sum up to 1, this is a weighted center of mass. So in the k-means algorithm, we had made a crisp decision, because that was cheapest under that model, to which cluster center a particular observation belonged. And we used those, so the probabilities there were either 1 or 0, and we used those to compute the center of mass. This time we have something similar, except that we now admit fuzzy cluster memberships. So the first term here, this would be, or this factor here, that's a cluster membership of observation I, how much it belongs, or to what extent it is associated with cluster J. So it's a number between 0 and 1. And well, we know that it's a number between 0 and 1 because it's a probability, so it's non-negative, and it's I can interpret it as a posterior probability, and summing over all of these must give me a 1. So this is where the normalization comes from. Now I have found an equation for an update of my of the means, but in the demo you saw that the cluster should also adjust the data in their shape. So we need to differentiate this entire thing with respect to the covariance matrix also. That is a little bit trickier. So first of all, the decision you have to make is, you see here we have the inverse of the covariance matrix, and there we have the determinant of the covariance matrix. The first decision that you have to make is with respect to what do you want to differentiate. It here will be easiest to differentiate with respect to the inverse covariance matrix. And I can rewrite this thing so as to make more obvious what this derivative should look like. It would be nice if we had this inverse covariance matrix at the beginning or at the end of a term, for example. So one thing I can do is, this thing here is a scalar. So this is 1 by 1. So if I want, I can insert a trace operator here without changing anything. The trace of a scalar is just that scalar itself. And then I can use the invariance of the trace under permutation to shift around the terms and obtain something where the sigma is at the beginning or at the end, like the following, for example. I'm also including this summation over the p's into the trace. So this is now the covariance matrix, sigma j to the power of -1, and it's followed by a summation sign, not a covariance matrix. This is my summation, which I had up here, ranging from 1 to n. Sorry about this typographic confusion. And now I've permuted these terms inside. I first have xi minus mu j, and then xi minus mu j transposed. Okay, the remaining terms were minus 1/2 the log of the determinant of my matrix, and the determinant was taken to the power of -1. Sorry. Okay. But I could write a plus here and a -1 there, because the log of A is minus the log of 1 over A. True. Thank you. Okay. Now, if you don't know by heart what the log of the determinant of a matrix is, if you want to differentiate it, then a good source is the matrix cookbook, your friend and helper. Here, for example, I can look up the linear form. So if I differentiate this, I get out that. And then you can also look up, what happens to the log and so on. All of this is the matrix cookbook, which you can find on the web. And taking all of that together will result in a great simplification. Namely, could we go back, please? I will get minus 1/2 of so now you see this was linear in sigma j to the -1, and the trace is very well behaved if you take the trace of a matrix and differentiate with respect to the matrix. So I get the following summation. Here comes the second term. This is now again my matrix, so my covariance matrix sigma j, and this is a summation sign. I want to set this to 0. This was using the fact that the derivative of the determinant of a matrix is the determinant of the matrix. Okay, and together with the log, it all means that everything here cancelled nicely, and we can finally solve for my updated covariance matrix sigma j. Is an expression that will also look reassuring. Good. This looks like an empirical covariance matrix. So if you remember first week of this course, this is how we estimated a scatter or an empirical covariance matrix, and these are again the same weighting factors that we've seen. So it's a weighted empirical covariance matrix, where the weights indicate to what extent observation I belongs to a component number j, and this is the covariance matrix j which we're trying to estimate here. So we are nearly there. We still need the mixture coefficients themselves. We need to remember the constraints that we had. In the end, it will turn out that they vanish, but we cannot know in advance. So up here we have, or on the previous slide, we have all these terms that do not depend on pi j. So I'm summarizing them here as terms that are independent of pi j, plus here we have the log of pi j, and then we need something to make sure that our constraints are respected. So I'm taking a Lagrange multiplier here, which enforces that they should all sum to 1. And I now take the derivative of this with respect to pi j, and oops, I forgot a multiplier, namely this one here. All of this needed to be multiplied with here these terms. The derivative of the log is 1 over pi j. And from my Lagrange term here, I'm left with a lambda. And I want to set the whole thing to 0. And I now multiply with pi j and sum over all of these j equations. These are a total of j equations. Or h equations which involve j. But our constraint was that the sum over j pi j should be 1. So all of these here sum to 1. And I'm left with lambda as minus the previous term here. I'm switching around the summation signs now. And this thing is 1, and this thing is n. So overall, lambda is minus n. Okay, this minus n I can now insert here and finally solve for pi j. So my pi j nu will be 1 over n So here we count for how many observations component number j is responsible for, well, weighted with this probability. Okay, and I guess I could have written a nu on these other equations also. Where are they? So I could have written a mu nu and a sigma nu. Okay, so overall we have something that's, so here are the fundamental equations, that's very close to what we saw for k-means, except that this time everything is probabilistic. Alright, so that was the M step, and the E step is very short. step is simply that the probability of component j given xi, using Bayes' theorem here, so it's pi j times the normal distribution evaluated at location xi, and the normal here is parametrized with mu j and sigma j, and this is divided by the sum over all these components. And these are also called the responsibilities. So this would be the posterior probability, or the responsibility that cluster J takes for observation number I. So the demo stays the same. Your interpretation of this is wholly different now. So there's different random initialization than we saw before. I first estimate the responsibilities, and they're reflected here by the colors. And the Gaussians are now updated to reflect those responsibilities. So this one will move down quite a bit. The blue one will probably move down. The red one will also become a lot more elongated. The green one will probably become elongated in that direction. And you see that the green one has also lost a lot of mass because it did not account for as many of the observations initially. And then we can reassign the colors and re-estimate the Gaussians and keep doing that until convergence. And you see that right now the solution is quite different from the one that we previously had, but it seems that up to permutation this time we fall into the same local minimum that we had before. So very few comments. You've seen that the whole theory in the background was not so easy, but the update equations which we get in the end are quite simple. So it's a method that's very easy to implement. However, it also has its pitfalls. So as always, EM finds only local maxima of the likelihood. And with Gaussian mixture models, there are actually some degenerate solutions which are a real problem. What do I mean by that? So let's say we have a few samples, and perhaps the proper solution here would be to have one Gaussian centered here, another Gaussian there. But what can happen is that you get one very broad Gaussian. Remember, they're all normalized to 1. So we have one very broad Gaussian that tries to explain all data. And then I have a single Gaussian which picks, any of the observations, let's say this one here, and makes this infinitely probable. Okay, so we will have some probability for all observations and infinite probability for this observation here, And since in the likelihood we take the product of all of them, this will diverge. So what you need is either a proper Bayesian treatment where you put a prior on your Gaussians, or at least a threshold where you say that your covariance matrix is not allowed to get less volume than something. So you want to prevent the shortest of these half axes of becoming too short. And then secondly, in high dimensional spaces, it is a good idea to not estimate the full covariance matrices, but to impose some restrictions on the structure of your covariance matrices. For instance, you can make them become diagonal or even isotropic. Okay, I also meant to talk about latent topic models today. Alas, there is no time. So what we have seen is density estimation, and actually these Gaussian mixture models are a very good method for density estimation also. I've argued how such non-parametric density estimates can be used for non-parametric classification or regression. I have not really explained how it works in the context of regression, but there is another Raya-Watson estimator that allows you to do so. And then I've talked about cluster analysis, briefly about one of these hierarchical crisp methods at some more length about k-means. And we've spoken about the expectation maximization and the Gaussian mixture model in great detail. So the thing to remember about EM is that it's just a optimization routine. So you have a model that involves parameters and hidden and visible variables. You can only observe the visible variables. You try to estimate the most likely setting of your parameters. You could use any method by just integrating out the hidden variables and doing inference. The advantage of using EM is that the equations that you find, they are sometimes better adjusted to the structure of your model than what a general purpose nonlinear solver can do. Well, we will see these Gaussian mixtures again when we talk about hidden Markov models towards the very end of the semester. Enough for today. Thanks for bearing with me throughout these long